Hello, very warm welcome to all of you. Good evening. After a very long time, we have decided to yes, I am welcoming you for the transfer function of the field control DC motor. As I had promised that I'll be doing all the videos. So here it is: transfer function of field control DC motor, controlled DC motor. So when I talk about the motor, basically what is a motor? A motor is a combination of a stator, which is a static quantity, and a rotating quantity. So the fundamental of the motoring action, if you look at the motoring action, so motoring action will take place if there is some static magnetic field. Inside that, we are producing an energizing an electrical coil or current inside the coil, and this is a permanent magnet. This is an electromagnet, and the rotation, a current carrying conductor in presence of a magnetic field will produce the rotation, which is the principle of the motoring action. So we have to understand this motor can be controlled via the rotating part in the DC machine, which is the rotating part is also called as the armature, whereas the stationary part where is called the field. In the stationary part, there is winding that is called the field winding. So a same motor can be run as a generator as well as a motor, a same machine. If the input is electrical, output is mechanical, the machine is called motor. If the input is mechanical, output is electrical, it is called as generator. And if it is running as a motor in clockwise direction, then as a generator also it will run in a clockwise direction. There is a misconception. If we run it as a motor in clockwise, then if we run it as a generator, it will be anti-clock. It's not so. It will be the same. Only thing, the reversal of the motor will take place if you are changing the plus and the minus sign. Okay, if you are altering the field winding of the motor. So before going to the motor, let me explain you the EMF equation for the motor is given by P phi NZ by 60A. Okay, so here you look in this 60A and your Z and the number of poles will be stationary, whereas the flux is okay. So P Z by 60A term is a constant term and the leftover term is N phi. So this value is called as K. So your motor equation can also be written as K phi N. Okay, this is the primary equation for the motor which can be written in terms of K phi N. And on the similar grounds, the torque equation for the motor is written as K phi IA. So before we go to the motor, wherein I'll explain you these are the number of poles. Poles means in the stationary part, the magnets that would be connected, those magnets are the poles, where the Z is the conductors on the field winding. Field winding is the stationary part. So this Z is given like, if you look at, yeah, if you look at these turns, so you see there is one side of the coil, okay, will have one turn, another side will have another turn. So Z would be equal to twice T. So this is basically for the motoring, the number of conductors for a single phase. Obviously, this is a DC, so it will be only okay. So 2T it would be representing wherein here N is the speed and this A is the armature parallel path. So these parallel paths are like, if you are giving one type of arrangement is like this, okay, and the another type of arrangement is like this. So here you see it's a lap connected winding. The number of parallel paths would be always equal to 2. Sorry, or wave winding. In the wave winding, the number of parallel paths would be always equal to 2. Whereas in case of the lap winding, the number of parallel paths would be A would be always equal to the number of poles. So we are interested in how to calculate the transfer function of the motor. Now, in order to calculate the transfer function of this motor, what we have to deal with, first of all, let me insert some blank pages over here. I don't think we have some more pages. So let me, no need of cover page. I have to insert a blank page. Insert blank page. Okay. So let this be. Now let me start it. Okay. Time and again it is asking for, okay, every page would require us to have this pen. Okay. Now let's suppose, let me draw the characteristic. Let me draw this motor. Okay. How it is drawn. Every motor is consisting of every machine is consist of electrical, mechanical and magnetic parts. So these parts are basically the electrical parts. This is the resistance. This is the armature part of the motor, which is the stationary, which is the rotating part in case of the motor. So herein it is represented like this. Okay, this is the motor part. This is the armature part of the motor. We are going to just derive the transfer function for the motor. So this is the armature part of the motor, wherein this is IA, this is the EA, this is the armature voltage. I don't know why this is getting, okay, yeah. This is your inductance, and this is basically primarily the motor part, how it is represented. Now we have certain terms here, which is mechanical torque, because at the end of the day, the torque will be getting produced, and we have the angular momentum, and we have the primary and angle theta, and that will be getting generated. And this is the field circuit. Here in calculation of this field circuit is of prime importance. So this is my resistance of the field, this is my field winding current, and this is my inductance of the field winding, and this is the field winding EMF. Okay, so if I write, first thing is that the torque that is getting generated inside the motor is proportional to, for the first thing, the flux path that I just forgot, because inside the motor the flux is getting generated, and this flux is proportional to the field current that is given as KFIF. And now I have the torque that is proportional to this phi f into IA. This proportionality constant I will replace by the term K dash, and phi f I can replace by equation 1. Suppose this be equation 1, this equation 2. So in equation 2 I have for phi f KF IF IA. So I take these two parts and I express this, the torque value Tm, as Km Kf Ia, wherein my K dash into, wherein my K dash into If, wherein my K dash into, uh, yeah, here K dash into Ia represents Km. Here there's one mistake, this should be If. So this is how my torque is expressed. Now, if I apply a differential equation to this part of the circuit, if you're looking at this part of the circuit, I can write the differential equation as LF DIF by dt plus R into IF would result into EF. And if I apply the corresponding, if I write the same equation in the Laplace domain, so in the Laplace domain, you remember the d by dt term is represented as S. The d by dt term is represented with S. In the Laplace domain, the same equation for this will become equal to S LF IF plus R IF is equal to E of F. And from here, I can get the value of IF in terms of EF. So I can write EF minus S. Here I can take this value common. First, let me take the value of IF, this value of IF common here, and then let's go about it. So I can write this as IF is equal to SLF plus RF is equal to EF. So once I'm writing this equation in terms of IF, I can write the equation for IF as EF divided by SLF plus RF. Now, one equation for the torque is this. Okay, the another equation for the torque in terms of the moment of inertia is given as Tm is equal to Gm d square theta m by dt square plus Bm d theta m by dt. So this is one more equation. So Bm d theta. So again, if I convert this into the Laplace domain, this equation, so this d by dt term will become s, and d square dt square term will become s square. So here I can write this equation as s square j of m plus s b of m is equal to Tm. Now from here, this equation, let this be equation 1, 2, and this be equation 3. Okay. And from the Laplace domain, the equation which we got here, the final equation. Okay, let this be 5. Okay. And then rearranging, we got the value of if is 6. So we can equate these equation. Tm is equal to Km Kf into if. So I can say that my term Km Kf into if, that is from equation 3, equate equation 3 and equation 7. Okay, so you can equate equation 3 and 7, and you can get Km Kf if would be equal to s square Jm plus sbm. So once you are equating these equations, now let me just join the another page. So you have these terms as, here you can see the value Km would be equal to this term. So yeah, let me take a pen. Okay, now Km Kf if is equal to, now we have the value of if. Let's substitute this value of if from equation 6. So substitute if from equation 6. What we have, Km Kf, instead of if we can write ef slf plus rf would be equal to s square Jm plus SBM. So this is the term that we are going to get. So one more important term over here was, see, this was in terms of S this was in term of S square, yeah. But the one more important term that we just forgot, because S square Jm, S square term was this term, but then the theta m term was missing there. So that theta m term, because in the beginning only I have just, if you look back, go to the slide, back side of the slide, yeah, here. So only d by dt is s, d square by dt is s square. So here when I'm writing the equation of the torque, so if you go back to the equation of the torque here, yeah, so you see that this theta m term I just forgot. This theta m term I have to mention, because this is s square Jm theta m, this is Bm s theta m. So theta m I can take outside, so this term would be theta m. Okay, and now what we have to do is, I have to get the transfer function. So the transfer function of this system would be in the mechanical domain. Output is mechanical, input is electrical. So this is a mechanical, and here the input is electrical. So theta m by e of f would be represented as, here s, here theta m will remain as it is. It would be km kf, okay, divided by ef term is gone there. You're left with s square Jm plus sbm divided by slf plus rf. So what I will do is that I'll make the term, this one of the terms over here, this you are seeing Jm s square term is there. This term, in order to make this term equal to 1, so what I do is that I take a time constant, in the time constant form I get a value of Tm, I write in terms of Jm Bm, and I also substitute one more value, Tf is equal to Lf Rf. So if I take this term Jm outside, okay, so what happens is this Km Kf would be equal to uh, to make this one, so it would be Jm. Okay, it would be S square plus S Bm by Jm. Okay, so if I take the term, sorry, if I take the term Bm outside, this Bm term outside, so it would be uh, S square Jm. Let me take into the next slide. Okay, let me show it in the next slide. So yeah, here it is. So we were with the equation here. Yeah, this is the equation here, that is theta m of s by E of s was given in terms of Km Kf. Then here the term was Jm s square plus Sbm, and here the term is Rf plus Slf. Okay, so if I take the term Rf outside, and here I take the term Jm outside. Okay, so what I'll do is that I take the term of Bm outside in the denominator. Once I'm taking the term of denominator, so I am left with Jm by Bm s square plus S, and here if I take the term Rf outside, so I'm left with here I'm left with 1 plus SLF RF. And again, can I take some terms outside? So this is my Km Kf. So now what I can do is that yeah, so I've taken the term RF and Bm outside. If I take the term S also outside, one of the S is also outside, so I'm left with Km Kf. This is your S term I'm taking outside, so it is RF Bm. So here it won't affect, here only one S gets reduced because this is S square term, so only one S. Here it would be plus 1. Since I've taken from here also one S term, I've taken here also. So what would be the remaining term there? So in case of the this term RF term, if I've it was like it was 1. So if I've taken the term S outside, so it will become LF by RF. Okay, and it becomes 1 plus, yeah, 1 plus LF by RF, LF by RF, right? So if you carefully analyze there, yeah, so this thing here can be written in this form. This Jm by Js can be written as, Tm can be written as Jm by Bm. Okay, similarly your Tf value can be written as LF by RF. So you have left with LF by RF value, and you have taken the S term just for this value. You have taken the S term, not for the other value. Okay, so you have taken S value here outside. Rest here it is 1 plus S LF RF. So this can be written in the form of Km Kf would be equal to RF. I'll segregate it. RF term I'm writing for 1 S plus TF, because your TF term is equal to LFRF. Then you are, then I further segregate it. I can write it as BM 1 plus STM into 1 by S. So this first term you can see over here is KF term. So this KF and 1 plus STF term here, and the second term would be Km, this value Km, and this denominator value into 1 by S. Now if I want to express the same in the block diagram form, so I can see my input value is E f of S is the input that is entering, and now I have the function, this kf function, which would be equal to rf 1 plus stf. Okay, then I have another function over there, that is my if of s, which is equal to your, after the if of s, the term there is if of s, the term there is km. Okay, and this term 1 plus stm. So after the 1 plus stm term, finally I have one term of omega m. So basically your omega m is what? Omega m, see, if you integrate, if you differentiate this, if you have s theta m, if d theta m by dt is your equal to omega m, so this would mean s theta m is equal to omega m, or in other words, sorry, yeah, so this theta m term, if you want to get from omega m, it would be 1 by s into omega m. So you are writing this omega m, that's why you're, in order to get the theta m, so you are writing 1 by s, and finally at the output you get theta m. So in the input there is e of fs, you can see this is the input, and in the output there is this. So this is from the block diagram algebra, this is the transfer function. And if you can look at the transfer function, this transfer function is basically an open loop transfer function. Hope you have enjoyed this session and liked it a lot. If you can subscribe, then you can subscribe. If you don't want, no issue,